Hi everyone, I'm Einar. I come from Norway and I work for the National Public Broadcaster. The agenda for today is the thing that you're seeing on the screen, which is a woodcutting by Escher called Square Limit. Of course, that's not the woodcutting, that's a PNG image of it. But what do you do? What I'm going to try to do is follow in some sense in the footsteps of Peter Henderson, who wrote a wonderful paper back in 1982 when I was 7 years old, and then he wrote a revised version of it in 2002, which is the paper that I've read. And in that paper, he shows functional decomposition and reconstruction of Escher's artwork. And so basically all the brilliant stuff you see here today is not mine, and the mistakes and misinterpretation, those would be mine. Yeah. And the inspiration for this talk comes from the Lambda Days keynote last year, a wonderful keynote by John Hughes and Mary Sheeran, where they talked about some influential papers on functional programming, and one of the papers they mentioned was Peter Henderson's paper. And I was sitting there in the audience, and I thought that, okay, this sounds really cool, and I think maybe I could try to implement this stuff in the language that I know best of the functional kind, which is F#. And I also seem to recall somewhere deep down in my brain that I've heard about this paper before in one of the video lectures on the structure and interpretation of computer programs from MIT. Where they also discuss Henderson's paper. They don't really reconstruct the square limit. Instead, they do transformations on this weird stick man called George. And so I implemented, from the best to my understanding, in F#, these combinators that Peter Henderson's defined in the paper. And that was kind of cool. And then I found out I wanted it would be even better if it could run in a web browser. And then I found some good people from the F# open source community had created this wonderful stack called Safe, which allows me, I'm not a safe expert in any way, but it allows me to sort of run my F# code in the web browser, so that's pretty cool. So huge thanks to them. And basically, this is the F# safe application running right now. So yeah, that's what we're looking at. So this talk is not an F# talk, and it's not a safe talk, really. I just use that because that's the things I know best. It's more a talk about abstraction, and in particular, functional abstraction in a way that composes well. So that's sort of the main lesson from this talk. So if these abstractions are important, what's the most important abstraction in this talk? That's going to be the picture. And the picture is not a collection of pixels or anything like that. In Henderson's paper, it's a function. And it's a function from some sort of box to a rendering of some kind. And the box you can see, hopefully, outlined here with a red vector pointing up to the left bottom corner, and then you have a purple thing and a pink thing. That sort of outlines the box. And yeah, let's take a look at the code. So here we have my picture type signature, which is going to be this function. And yeah, let's look at what a box is. So a box consists of 3 vectors, the red and the pink and the purple one that outlines the box. And a vector is very simple. A vector is just 2 floating numbers. It sort of outlines how far you have to go in the x direction and how far you have to go in the y direction from wherever you're at. And I've also overloaded some operators that allow us to add vectors and negate vectors and subtract vectors and so forth, and also scale vectors by some scalar number. So if I scale it by a factor of 2, I get a vector that's twice as long. Okay. So much for theory. Now, the interesting thing here is that when I have a picture like this F here, maybe we should take a look at the definition of F. The F shape is really just, it's defined in terms of the unit square. And then there is some magic going on that sort of stretches this into fit whatever box I give it. So if I start stretching this box, like changing these vectors basically, it's going to look different, hopefully. Let's see if things work. Yeah. So it sort of magically adapts to whatever box you give it, which is kind of cool. We're not going to look at the details for that. You can see the code later. It's not complex in any way, but we're going to have to choose what we look at. Right, and I also have this. Let's see. Yeah, that's the Stickman George. So I copied that from the SIGP lectures. So, so that's the picture, but I want to define transformations on that picture. And basically, since I have this magical picture that adapts to whatever box I give it, when I want to do something like turn this thing counterclockwise 90 degrees, all I really need to do is turn the box. Right, so let's try. So I want a function called turn that takes a picture and returns a picture. But I can create that very easily. If I have a function called turnBox that takes a box and produces another box, I can just compose that with whatever picture I'm given, and that's going to be it. So let's try turnBox. Yeah, so how do I turn a box? Maybe we should take a look at that. So turning the box now really amounts to moving the red arrow to the bottom right corner and then sort of adjusting the other vectors accordingly. And I have the arithmetic for that here. It's quite simple. So that's what I need to implement. Let's see, something like this. And I have my turn function. Then I have basically one code file per page or slide in my deck. So turn letter, and just to show how the box also turns, I'm going to render that as well. So let's see if this updates. Sometimes I have to kick it a bit. Let's see. Yeah. So now I sort of turned the picture, and all I really did was turn the box. I'd like to generalize that a little bit. I'm going to write a helper function, which is going to be allow me to apply some sort of transformation many times if I like to. So I'm going to compose the function that I give it 0 to n times. So yeah, I'm going to do something like this. And if I compose it 0 times, it's going to be the identity function, which does nothing, right? So I can do turns, which does turn n times. Now I can do something like this. Well, turns, not turn. And I didn't, well, I can just do this to turn the box 2 times, right? Let's see if that works. So hopefully it turns twice. Yeah. Okay, so that's the first picture combinator, or transformation, really. Very simple. Now flip, I'm just going to take the picture and do this, basically. And again, I can do that just by manipulating the boxes. So I'm going to create, similar to before, something called flip box, which is just manipulating the vectors here, even simpler than before, really. And I'm going to have a flip function, which is just composing the flipbox function with the picture I give it. Okay, let's do flip. And flipbox just to see what's going on. And let's see, yeah. And of course, flipping twice is just going to give me the original picture back, so there's no point in doing that. Instead, let's do toss. And it's not called toss in Peter Henderson's paper. It's called rot45. But it's sort of, it looks a little bit like tossing something up into the air. And if you look at the arithmetic here, you see that the new A vector, the red vector, should go to, okay, A plus B plus C. Oh, maybe you don't see that. Well, yeah, you do. B plus C cut in half, so the A, the red arrow, should point up here, right? So, okay. Yet another transformation of boxes. And okay, just to avoid making mistakes, I'm going to copy this. And this is now my specification. Yeah. A plus, yeah. And B plus C divided by 2. And finally, this. And yeah, I need to do this again. Okay. And throw this up into the air. And actually, I'm going to leave the original box just to see clearly what's going on. So I'm going to draw 2 boxes now. Let's see if this works. Yeah, so you can see what's going on. That's the original box and the box when you throw it up into the air. So that was toss, which is the final sort of simple transformation we're going to do. Now we're going to try to combine simple pictures. So I'm going to define a combinator called above, which just puts one picture on top of the other one. So let's see. Actually, I'm going to start by a more general function called above ratio. And the thing with above ratio, it's going to take weights that you sort of assign to each picture. So the above thing would just split it equally in half, right? But you can imagine you want to have a greater share for one of the pictures. And above ratio, what it's going to produce is a picture, and a picture is just a function from a box to a rendering. So it's going to be a box. And then I'm just going to compute the fraction that I'm going to assign to the first picture. So that's going to be a float m, and something like this. And then I'm going to split the box I'm given according to that fraction. And when I'm done with that, I'm going to pass the first box to the first picture and just append it with whatever I get from passing the second box to the second function. But I don't have this split vertically function yet. So that's something I do with the boxes. So split vertically. Oh, let's see. Yeah. And that's going to produce 2 boxes. Well, the top box is for the first picture because that's going to be on top of the second picture. So I'm going to have to move that upwards. And how much? Well, I'm going to have to move it with as much space as I use for the second picture. And then I'm going to have to scale it also according to the fraction assigned to the first picture. And then the bottom picture is going to be, I don't have to move that because that's going to be in the same place. But I'm going to have to scale it. And yeah, basically just return these. Now I don't have these implemented yet. Let's see. It's very simple to move something here. I just have to add the appropriate amount of basically going up. And yeah, scaling vertically, so that's just going to be scaling the vertical vector and leaving everything else intact. So that's what I need for above ratio. And then it's very easy to define above, because above is just above ratio with equal weight given to each of the pictures. Right? So let's see here. Okay, above. So I'm going to try to put the F letter on top of a turned version of the F letter. And just to see what's going on, I'm going to call split vertically once more. And just split the box in half so we can see what happens. Let's see if it works. It seems to work. And of course, I can keep doing this. So what happens if I do, okay, above, and then something I turn this letter 2 times, right? Well, if I want to see what's going on, I'm going to have to split the lower box also to see what's given to each picture here. Yeah. Something like this. But it's important to remember that these boxes that I'm drawing, those are just sort of helper lines to understand what's going on. What we have here is really a picture, a single picture composed of these three parts. So I can treat it just like any picture. So I can say, okay, I'm going to take this, and I'm going to turn it. And what I really pass to that picture is this box, the original box. Let's see what's going on now. Yeah, so I can treat it just like a picture. And yeah. So that's above. Let's see. Beside is very much like above. So it's above puts things on top of each other. Beside puts a picture to the left of another picture. So we can sort of, it should be very easy to implement. So I can just do exactly the same thing. I'm just going to steal this. Say, okay, it's going to be beside ratio. I'm going to split the other way. And yeah, beside, and yeah. I do need to implement this, though. So the left box. This time I don't have to move this one, because that's sort of where the original box was, but I have to scale it. Oh, it's not vertically. It's like this and right. And I have to move this one. Okay. Left and right. Well, a little bit tedious this now. Move. So just like before, but by adding it to a scaled version of the horizontal vector. And same thing here. Yeah, F times B, and we should be done. And let's see, beside ratio, and my beside page. So let's see, flip. And hopefully we see something flipped. And we don't, so I have to kick it. Sorry. I think it's something about the timing of when I press enter and save and stuff like that. It sort of comes back to bite me at times. Well, there we go. So that's beside. And yeah, we spent 20 minutes. It's sort of like half the talk, and this is where we got into. It's a sad thing, but the nice thing with these abstractions is that they compose very well. So at this point, we're ready to sort of leave the low-level world of vectors and mostly boxes behind, and we can define higher-order combinators using the stuff we've defined so far. So next combinator is quartet, which is to create a quartet out of 4 pictures, and a quartet is a 2x2 grid. It is, let's take a look here. It's basically this, right? You combine 4 pictures into one. So I'm going to need, well, let's see. I need a quartet function. This was the wrong file. This is the correct file. And it's almost embarrassingly easy to create quartet, because now I have beside and above, and I'm done, right? I just squish what I call the northwestern picture together with the northeastern one into one, and the southwest and the southeast, and place them on top of each other, and that's it. Let's see. Northwest thing is going to be the stick figure. Well, southwest and southeast. And let's see if I can recall the transformations to create the piece of art that was created in the 6P lectures. Let's see if it works. I think that's the same thing. Let's double check. I think it's the same thing. It's the same weird thing. So that's pretty cool. We were able to take 4 pictures and combine them into one. But the really, really cool thing about this is that these function abstractions have this property that they're closed under the means of composition. And what that means is that when I've created a picture like this one, it's still just a picture, right? So I can sort of keep composing arbitrarily more complex pictures with very little effort. So I'm going to try to do something like that. So I have a picture called blank, which is basically renders nothing within the box that you give it. Oh, well, it's going to be a quartet, obviously. So a quartet of a blank, and then 2 pictures, and then blank again. And I'm going to have something that takes a function that takes a picture and just creates a quartet out of that picture. So let's see what we can do with that. I'm going to pass my original quartet to the pattern, and then I'm going to 2 times apply this QQ thing. Yeah. I think it's lying to me with the squigglies. Sorry? It should be. You're absolutely right. Thank you. It's not lying to me. It's yes. So it's very easy to create, well, not necessarily the world's most interesting image, but at least more complex than what we had before. Next one is very similar to quartet. It's a no-net, which is a 3x3 grid. So it takes 9 pictures and create 1 picture out of it. And that's basically the skeleton that we're going to use for the square limit. So the square limit is going to be a no-net of some kind. Let's see. Yes, the no-net. Right. So the no-net takes 9 pictures and creates 1. So obviously, I can do this in a similar way as the quartet, but I'm going to generalize a little bit. So I'm going to create a recursive function called row, and that's going to be a function that takes a list of pictures and sort of squishes all of them together into one. So if I give it no pictures, then it's going to be the blank picture. If I give it at least one, then it's going to be, well, the side ratio. And then I'm going to allocate one space to the one picture and sort of as much space as I have elements left in my list of pictures. So something like this, and just call myself recursively. And I'm going to do exactly the same for column. That's going to be above ratio and call column. Now, if I sort of structure my data a little bit, let's see. Yeah, like this. So now I have a list of rows, so I can sort of map the row function over that, and then I have a column of pictures, basically. So I can just pass that to column, and then I have my no-net. Let's see if that works. It doesn't, so I'm going to kick it again. Oh, let's see. Yeah, so 9 pictures turned into 1. And again, this is like a nicely composable thing, so I can create, I don't know how to call this, but something like this. I'm going to just replace the middle picture with the picture that I give it, so I can do zoom. So I'm going to zoom in 3 times on the middle picture, in a sense, and we have something like this. Right, and yeah, we still haven't seen a single fish. It's time to introduce the fish. This is my attempt to reproduce the fish as it looks in Henderson's paper. And I'm going to create a combinator called over, which just renders, well, 2 pictures, it says here, inside the same box. I'm going to just generalize it and take a list of pictures and draw them all inside the same box. So it's quite similar to above, in a sense. So over, and given a list of, let's see, twice a p and a twice turned p. So over, take a list of pictures, and it's going to produce a picture, so that's going to be a function from a box to something. And basically, I'm just going to do a collect over the list of pictures and pass the box to each picture. And then this collect thing is like flat map, so this is going to produce a list of stuff, which is my rendering, and then I have to squish all of that together into one rendering. Yes, so let's see. So fits nicely with itself. So there was some thought was given into designing this fish. Now I'm going to create something that Peter Henderson calls the T-tile, which is one of the sort of basic building blocks in the square limit. And T-tile takes, well, a picture, but it's going to be a fish, so I might as well call it a fish. It's going to use over, but it's going to add 2 more fish. So it's going to add first it's going to add a north fish, which is sort of placed on top of the first fish. We can see, or we can try to see, how that works out. So t-tile. And yeah, let's see. There we go. So that's the north fish, but we're going to add one more fish, which is going to be the eastern fish. Let's see, pictures. And I get the eastern fish by turning the northern fish 3 times. Yeah. Okay, so that's the t-tile. That's one of the fundamental building blocks for the square limit. And then the second one, and the second and final one, is the u-tile. There's just 2 of them. The u-tile looks a little bit different. So yeah, it's going to call over, and it's actually going to take the northern fish. It has that in common with the t-tile, but it doesn't use the original fish. Instead, it needs a western fish, which is turning the northern fish, and it's going to have a southern fish and an eastern fish as well. Basically, just adding one more turn to each. And I didn't, let's see, I'm going to have to call the u-tile as well. Let's see what it looks like. Yeah, it's 4 nice fish. And you can see that 2 of the fish are actually the same as in the t-tile. We will replace the big fish with 2 smaller fish. Now, I said that the square limit is a no-net, and it consists of 9 pictures. 4 of those are sides, so those are going to be similar. 4 of those are corners, also similar, and then something in the middle. So we're going to do the side first. And the side is going to be a recursive function. Let's see. It has for the degenerate case, it's going to return a blank picture. Otherwise, it's going to call itself recursively. And it's going to use a t-tile also. And then it's going to be a quartet. But what we're going to put in here are 2 instances of the recursive call to side that might be blank for the sort of the northwest and northeast picture, and then it's a turned t-tile for the southwest picture and just a t-tile for the southeast picture. Yeah. Let's see. Let's do the boring case first, which is going to have blanks on top, just to see what's going on. So we have sort of you can see the turned t-tile there, and you have the regular t-tile. But it's more interesting once we start to sort of add layers of recursion, because you're going to have exactly the same figure applied on top of each one of those, right? And then you can keep going for as long as you like. Yeah. Seems reasonable. And then, yes, the corner is quite similar to the side. So corner, I'm going to do the boring case again with just basically no recursion. Yeah. That's another recursive function, and there are actually 2 cases of recursion for corner. So it's going to recursively create a corner and a side. And again, For the base case, it's just going to return blank pictures. Otherwise, it's going to call itself recursively. And it's another quadrant. So to the northwest, we're going to place another corner. And on top, to the northeast, we're going to place a side. And then we have a turned side. And finally, the U tile. Let's see. Yeah, just missing equals. And it's not called fish, it's called P. Let's see if we get a corner. It's going to be a boring corner in the beginning. That's just the U tile. We can add, so it's going to be a side on the top and a side on the side, and another corner in the corner. And we can keep doing that as well, for as long as we like. And with that, we basically have all we need to, let's see, oh. Yeah, create the square limit. Let's see. So the square limit is consisted of corners, sides, and something in the middle. So northwest corner, just the corner. Yeah. To the northeast, I'm going to have to turn the corner 3 times. And something like this. In the middle is just another U tile. Let's see if I can type this correctly. But you can see it's just turning the sides and the corners a varying amount of time. And it's a no-net, so like this. And let's see. This should give us the square limit. So this is my replica of Henderson's replica of the square limit as an SVG. But it's, well, there we have it. It just takes a little bit of time because it's the SVG is turned large. That's sort of the thing. So this is very cool, and you can see that structure-wise, it really captures the essence of Escher's work of art. The only thing is that, okay, you can see the fishes, they're not quite the same. They have the same shape. They don't look exactly the same. So I was wondering if I could do something about that. So I tried to do something. So I created another fish with essentially the same shape. This one is a white fish, and then I added something called a hue or color. So let's, yeah. And instead of boxes, I created something called a lens. It's not a functional programming lens. It's just a box and a shade of color. And the hue is either blackish or grayish or whitish to sort of represent 3 different kind of states of color for a fish. Let's see. So this is essentially the same code I've just written, but just with this additional thing where you have a combinator that lets you change the color of a hue, right? So I'm not just transforming the box, I'm also changing the color. Right, so I have, well, I have a new definition of picture that takes now a lens, which is just a box and a hue, and produces a rendering out of that. Yes. So with that, we should be able, if I give it a little bit larger box. I have this rehue function that I can call on my fish, and well, it needs to be a row, right? We had this row function. And this should give us 3 versions of the same fish. And using this, we should be able to, well, create, it's a little bit sluggish now, another version of a square limit with these 3 fish, which is really just the same fish with different coloring. Let's see. Yeah. So another version of square limit. Let's see if it works. Come on. Yes. And that's basically what I have. So, thanks.
Well, I think that was the best example of live coding I've attended, at least.
Oh, thank you.
I think we have time for one question.
If you're interested, I'm not sure if I'm online, but the code is here. Safe-fish. I'm going to post the GitHub link on Twitter, I think. So if you're interested, you can download it. I have a bunch of branches that you can sort of check out at different states and sort of live coding through it. So that was in case I was going to screw up something majorly.
Okay, I see there's one question, and since we have time for it, I'll just pop over.
No kittens? There are no kittens. It would have been a catastrophe to have kittens here, I think.
Do you know of any similar work using constructive solid geometry?
Sorry? Using what?
Constructive solid geometry, CSG.
I don't know what that is, so I'm going to say no, unfortunately.
Okay.
But if someone could tell me, I would absolutely be interested, but so, no.
Presumably it's the same sort of thing, but in 3 dimensions? Yeah.
Yeah, a three-dimensional version of the same thing, yeah. I think there are people working on some seriously cool stuff, but I'm not familiar with it, no.
Okay, so let's give... Oh, all right, one more.
So, did you think about fish design, so to say? Because there are certain constraints that have to do with the way you rotate, etc.
Obviously, Escher thought a lot about it. There are various tessellations that you can use to sort of fill a surface like that. I was looking for alternative shapes that were equally interesting. I'm not sure if I found them, or at least I didn't quite know how to adapt the approach to, well, the fish is in some sense confined to a triangle, right? And then you have some variations that makes it fit nicely into itself. Yeah. I was looking for it, and I have done some simple things with simpler tessellations. So you have like a lizard shape that's also Escher created that you can use with some of these transformations.